Hello, good day. This is the simulation project proposal to be presented by Alos, Bintaha, and Lidama. And this is the group 6. Today we are going to discuss about the gas properties to be introduced to us by Alos.
Introduction. According to life science, gas is one of the three traditional states of matter, the other is liquid and solid. Gas is a state of matter that has no proper shape and no definite volume. Gases have lower density than different state of matter. The particles move extremely quick and crash into each other, making them diffuse or spread out until they are equitably disseminated through the volume of the compartment. Gases have three trademark properties. Number 1, they are not difficult to pack. Number 2, they extend more space than liquid and solid. And number 3, they consume definitely more space than liquid and solid. The study of gases permits us to comprehend its properties and its least complex. Individual particles acting freely, totally simple by collaboration and the impedances between one another.
Thank you, Alos. For you to continue that, let's look on the learning objectives. In the end of this activity, students will be able to first determine how changing a variable among P, which means pressure, V or volume, N, and T influences other gas properties. Number 2. Predict the speed of molecules in the thermal equilibrium based on the relative masses of molecules. And lastly, identify when pressure, volume work is done by gas. Now, let's welcome again Adrian Carlos to tell us about these basic concepts. Adrian?
Basic concepts. Compressibility. Gas molecules are able to be compressed or pushed closer together. This compressibility occurs when the volume of a container is decreased. As the volume decreases, the gas molecules move closer together. This also means the pressure increases. Example of this is the scuba tank. Scuba diving is a form of underwater diving in which a diver carries his own breathing gas, usually in the form of a tank of compressed air. Compressed gases are used in many situations. Expandability. Gases expand to fill their container. This means the air contained in a balloon fills up the entire balloon and does not remain in one single spot of the balloon more than another. If the balloon was popped, the gas molecules would expand to fill the space of the room. This also means that the space or volume a gas occupies is inversely related to pressure. If the gas in the balloon has a smaller volume and higher pressure, but when let into the room, it has a larger volume and lower pressure. Volume is simply the space in which the molecules of the gas are free to move. Pressure is also affected by the volume of the container. If the volume of a container is decreased, the gas molecules have less space in which to move around. As a result, they will strike the wall of the container more often and the pressure increases. An increase in the number of gas molecules in the same volume container increases pressure. On the other hand, a decrease in container volume increases gas pressure. The volume of a gas can be measured by trapping it above mercury in a calibrated tube known as a gas burette. It is important to bear in mind, however, that the volume of the gas varies with both the temperature and the pressure. Pressure. It is a force exerted by the substance per unit area on another substance. The pressure of gas is the force that the gas exerts on the wall of its container. When you blow air into a balloon, the balloon expands because the pressure of air molecules is greater on the inside of the balloon than outside. Pressure is a property which determines the direction in which mass flows. If the balloon is released, the air moves from a region of high pressure to a region of low pressure. If the gas is heated, its particles move around more quickly. They hit the walls of the container harder and more often. This increases the pressure. Sometimes, the pressure gets so great that the container bursts. That's why the balloons and tires burst if you blow them too much. Temperature. An increase in temperature of a gas in a rigid container increases the pressure. If two bodies are at different temperatures, heat will flow from the warmer to the cooler one until their temperature are the same. This is the principle on which thermometry is based. The temperature of an object measured indirectly by placing a calibrated device known as a thermometer in contact with it. When thermal equilibrium is obtained, the temperature of the thermometer is the same as the temperature of the object. It would be very unadvisable to place a can of soup over a campfire without venting the can. As the heat's up, it may explode. The kinetic molecular theory explains why. The air inside the rigid can of soup is given more kinetic energy by the heat coming from the campfire. The kinetic energy causes the air molecules to move faster as they impact the container walls more frequently and more force. The increase in pressure inside may eventually exceed the strength of the can and it will explode.
So this is Eileen Lidama, and now to further understand what is the gas properties, it is very important that we know or we have an idea on the formulas that we can use in this lesson, because these formulas will help us understand what is the relationship between one property of the gas to another property of gas. So now we have the Charles law, which gives the relationship between volume and the temperature. So here the relationship of volume and temperature is directly proportional. That means if the temperature increases, then the volume of the gas increases as well. So if the temperature of gas decreases, then the volume of the gas decreases. And we also have the Boyle's law. So in Boyle's law, it states that the volume of a given amount of gas held at constant temperature varies inversely with the applied pressure when the temperature and mass are constant. So meaning the relationship of the volume and the pressure is inversely proportional. So if the volume increases, then the pressure decreases. And if the volume increases, then the pressure decreases. So we also have the Avogadro's law. It gives the relationship between volume and amount of gas in moles when pressure and temperature are held constant. And if the amount of gas in a container is increased, the volume increases. If the amount of gas in a container decreases, the volume decreases. So the relationship of these two is directly proportional. Now we also have the Gay-Lussac's law, which explains the relationship between the pressure and temperature. It states that the pressure of a given amount of gas held at constant volume is directly proportional to the Kelvin temperature. So meaning, if the pressure increases, then the temperature there increases as well. So if the pressure decreases, then the temperature also decreases. So one important also is the combined gas law moving forward. So in this this law, the combined gas law allows you to derive any of the relationships needed by combining all of the changeable pieces in the ideal gas law, namely the pressure, temperature, and volume. And note that the number of moles do not appear in this equation because it is generally constant and therefore cancels since it appears equal amounts on both sides of the equation. And the general formula in the combined gas law is the P1V1 over T1 is equal to P2V2 over T2. So that's it for the related formulas on this simulation.
And to continue, of course, this is I, Rizal Joy Bintaha. So, in the flowchart diagram, this is the PhET simulation of gas properties. When you enter the simulation, you will search for the gas properties, and then the first one, you'll click on it. So, there are choices, and now we are going to the PhET simulation. Now, we are here at the PhET Interactive Simulations. And then as you've entered, you're gonna search for the gas properties. Okay, it is now loading for us to be able to see what is really happening during the simulation. So first, we are going to the ideal. So in the ideal, you can select nothing or you can control the volume. Let's go to the volume. Okay, in the up, you can check the collision counter. Okay. Then you can also change the mass of each particles. Now, if we pump here, okay, let's pump some gas in there, the heavy side of the gas, we can see that the mass is increasing as the number rises up, the mass is increasing. So how about the red one? Same, we go into the collision counter. And then we're gonna pump. No, that's wrong. Let's pump with the red one. Okay. It is also increasing. This is gonna what? This is gonna support the statement that as many particles there is, the mass rises up. Now, we can see here that if we'll pump here any of the particles, the heavy and the light one, then we turn the cold or cool, we cool them. Okay. Their movements have been slowed down and the temperature slowed down too. Okay, some may say it is because that they are heavy and light. How about the heavy one? Okay, at first we viewed them both. Now we'll see now that the temperature and the pressure is rising up, and then we cool them down. You can see the temperature and the pressure is going down, as well as even if it is the light gas kind of gas where the speed is very much fast. If we for example count the collisions of the heat, if the box is heating, then we can say that there are more than or nearly 2,000 of that. Now let us explore more of the other. This is explore. Here we have also the collision counter, which is we are going to be needing, and of course the heavy and the light. Here we can change if it is Kelvin and Celsius. So all of this in the explore one is in the ideal one. So let's continue to the third one. This is the energy. Okay, so we have here stopwatch and width. We have particles. We have collisions here. We had injection temperature. Now, if we pump gas to that, here we can set on this side, we can see the average speed of that of the blue one. And we can see the pressure and the temperature is rising up. If we look at the kinetic energy, now if we restart that and then we put then we heat up that, then the speed. So this is to prove that something, if we heat up in the continuation, we can see that the speed is rising up as well as the temperature. Okay, and the diffusion, this is the final one out of the four. Here we can add and we can subtract the number of particles, mass, radius, and the temperature. Now we have here the center of mass. We're gonna check the partial flow rate. And now we're gonna add there 20. We're gonna add the same number and 60. Let's add the data. Okay. Now if in the normal one, if we remove the divider, the light one goes first into the other one versus the blue one. So as can you see the arrows, it is explaining how the gas moves. And if you go on further with this, you will understand more how the gas particles of the temperature, volume, and pressure, and mass, and everything that in this will be able to affect each other. And for the last one, I was not able to demonstrate it to you earlier, had that the volume. Okay, now we're gonna pump. Now, gonna volume, have that. It's opening. The temperature, the pressure, and the here if the volume is small, or the container of the gas, the pressure rises up. A little small. Okay. The pressure and the volume. Now we don't have the now it's different here. Now if you go on further with this simulation, you will understand how the volume affects the pressure and the collision counter and the speed of the gas, and also in the energy. I will explain that the higher these gases, the higher of the temperature, the increasing of its speed, and the greater force it will hit this box, and that will form as a pressure. Then it will heat and heat as repeatedly the box will explode. That is their relationship. Thank you. Going back to our flow chart, that is why we here see that we should observe on the changes on the temperature, volume, and pressure on the gases. Now, all in all, that was the gas properties. And again, thank you for watching. And this is Alos, Bintaha and Lidama of Group 6.